We just talked about oxygen transport, so it makes sense that we'll talk about carbon dioxide transport. Unfortunately, I don't have a Mean Girls analogy to talk about with this one, but we'll still get through it just the same. And so with this one, we actually have several outcomes. This one looks scary, but I'm going to try and go through this slowly. We'll definitely cover this in class, make sure that you understand it. So just have some trust in me, we can get through this. So when it comes to carbon dioxide transport, it's transported in 3 ways. 2 of those ways are the exact same as oxygen, but one way is different, and that's bicarbonate. Okay, most of our carbon dioxide is converted to bicarbonate for transport. And we do this because we don't want it to bind to hemoglobin, because if it's bound to hemoglobin, then oxygen can't bind to that hemoglobin. There's also some carbon dioxide that's dissolved in plasma. The issue with carbon dioxide being dissolved in plasma is that carbon dioxide is an acid, and so that will make us more acidic. And that ties us into this equation. This is one of the few chemical equations we will talk about in this entire class. Okay, so let me walk you through this. So we've got CO2, or carbon dioxide, plus water, with the help of an enzyme called carbonic anhydrase, will be converted into carbonic acid. Carbonic acid then breaks down into bicarbonate plus hydrogen ion. Now, as you can see, these arrows go in both directions, meaning that this is a reversible reaction. And so this equation will move towards the bicarbonate side when we produce carbon dioxide. The reason that we want it to go this way, or one of the reasons, is because we want to convert carbon dioxide into something that won't take up space on hemoglobin for transport. However, when we get to the alveoli, this equation shifts back towards carbon dioxide so that we can have that carbon dioxide diffuse into the alveoli and we can breathe it out. Okay? Ultimately, we're trying to find a balance or a steady state between the amount of bicarbonate and the amount of carbon dioxide. We'll talk about this more in a few minutes, but carbon dioxide, like I mentioned, is an acid. Bicarbonate is a base. And so we can use these two to make sure that our pH in our bloodstream is where we want it. So we've got these pictures. On the left side is showing you what's going on in the tissues. On the right side is showing you what's going on in the alveoli. Okay, and so the red circle in the middle is a red blood cell. There's a lot that's happening on this red blood cell. And we're going to go through each half of this, or each of these panels now. So we're going to start off by what happens in the tissues. So carbon dioxide is produced by the tissues during metabolism. That carbon dioxide will then diffuse into the plasma. Okay, but once it gets into the plasma, we need to keep some of it in the plasma, some of it will bind to hemoglobin, and most of it will be converted to bicarbonate. So let's talk about how we get there. So some of this carbon dioxide, like I said, is going to stay in the plasma. However, a lot of it's actually going to diffuse onto the red blood cell. Now, when it diffuses onto the red blood cell, there's a couple of things that can happen. Okay, one, it will just bind to the hemoglobin. Okay, and this isn't the end of the world. It's okay if some carbon dioxide is bound to hemoglobin. We just don't want excessive amounts of carbon dioxide binding to hemoglobin. The other thing that will happen is that carbon dioxide will combine with water and form carbonic acid. Remember that equation a couple of slides ago. Again, this is helped by the enzyme carbonic anhydrase. Okay, so we're going to forget about the stuff that stays in the plasma, and we're going to forget about the stuff for now that's bound to hemoglobin. That's pretty easy. All right, so we've got this carbonic acid. It breaks down into hydrogen ion and bicarbonate. We don't like hydrogen ion floating around just by itself because it's acid, and acid burns stuff, breaks proteins. Okay, so what's great is that hemoglobin will pick up that hydrogen ion. The downside is that's one less seat for oxygen to bind to if hydrogen ion's already there. But we don't have acid on the loose. That bicarbonate will then leave the red blood cell, and it goes into it's pumped into the plasma, or diffuses into the plasma, but in order for it to go into the plasma, it needs to be exchanged for a chloride ion. Bicarbonate has a charge of -1, chloride has a charge of -1. What this ultimately does is make sure that we don't change the charge of the red blood cell, because if we change the charge, we can change a bunch of other things. So there's no change in charge, say that 10 times fast, when we exchange bicarbonate for chloride. Then we get to the alveoli. Guess what happens? The exact opposite. Everything goes in reverse. So, bicarbonate that's in the plasma now swap back onto the red blood cell. Again, we're exchanging it for a chloride ion to maintain that charge. That hydrogen ion that's bound to hemoglobin will separate from the hemoglobin and combine with the bicarbonate that's just entered the red blood cell. Now we've got carbonic acid. Well, that carbonic acid, again with the help of carbonic anhydrase, it's an interesting enzyme that helps both ways, will break that carbonic acid into carbon dioxide and water. Okay, so now we've got carbon dioxide, which we want to get rid of, and we've got water, which is just water, and we love water. Okay, so the not carbonic, but the carbon dioxide that we just formed from the breakdown of carbonic acid can then diffuse into the plasma. Okay, that carbon dioxide that was bound to hemoglobin can separate from hemoglobin and diffuse into the plasma. Then we've got carbon dioxide that was already in the plasma. And so all of this carbon dioxide that's in the plasma, it's going to go from high concentration or high pressure to low pressure. So high pressure in the bloodstream into low pressure in the alveoli. Okay? And as a result, it gets into our alveoli, we breathe it out. That's the main idea of how carbon dioxide transport works. So, remember that I mentioned at the beginning, carbon dioxide is like an acid. Let's talk a little bit about acid and pH and hydrogen ions. pH is ultimately a measure of hydrogen ion concentration. This is how you calculate it. You'll never have to calculate it in this class, but it's the negative log of hydrogen ion concentration. Because it's a negative log, as hydrogen ion concentration goes up, pH goes down. So high concentration of hydrogen ion means it's an acid, but that leads to a low pH. Okay, so we're going to talk about this more in a couple of weeks when we talk about acid-base balance. So let's talk about carbon dioxide. As I mentioned, carbon dioxide is a weak acid, so if I have more carbon dioxide, I have more acid, which means my pH is reduced. If I hyperventilate or breathe more than normal, that means I'm getting rid of more carbon dioxide, and so as a result, I'm getting rid of acid, my pH goes up. The opposite happens when I hypoventilate or breathe less. Then we've got bicarbonate. Bicarbonate is a base, or it's alkaline. Okay, so if I have more bicarbonate, I have more base. And yes, Megan Trainor's going through my head right now. And so if I have more base, I have a higher pH. If I retain bicarbonate, I have a higher pH. Unsurprisingly, if I get rid of or excrete bicarbonate, and I do this through urination, my pH will be reduced. And so ultimately, like I said on that slide when I first showed you that equation, we're trying to maintain a good value or a good relationship between the amount of CO2 and the amount of bicarb so we can keep our pH at normal. Last thing, carbaminohemoglobin. It'll get you a lot of points and words with friends. Okay. This is what carbon dioxide, or what happens, what is formed when carbon dioxide binds to hemoglobin. Okay. Now, to be clear, carbon dioxide doesn't sit in the same seats that oxygen does. However, when carbon dioxide binds to hemoglobin, the shape of the oxygen binding site changes. Okay. So it's like when I'm sitting, there might be a space in between me and my wife when we're sitting on the couch, and then Asher comes in and sits down. Okay. It's not as comfortable. It's a little more difficult. And so one of us will likely move just to make space for Asher. Hemoglobin plus CO2 equals carbaminohemoglobin. So with this, can you do these three things? Can you identify the main ways that carbon dioxide is transported? Can you state that chemical reaction that shows the relationship between carbon dioxide and bicarbonate? And can you describe how carbon dioxide and bicarbonate both affect pH?